Today we'll be working on the following problem. Let X, D be a compact metric space where D is the matrix. Show that there exists m greater than 0 such that D of xy is less than or equal to m for all x and y in X. Part B is like let X D be a complete metric space, m greater than 0, and we know that D of xy is less than or equal to m for all x and y in X. So the question is X with this D necessarily compact? So pause the video if you want to work on this problem by yourself. Okay, let's see for part A. We want to prove that. So basically we can pick a particular x sub 0 in X. Of course, here we assume X is non-empty, right? So we look at all these open balls centered at X sub 0 with radius n, where n is an integer. And this is the set of all y in X such that the D of y x sub 0 is less than n, all right? So these are all the open balls for n equal to 1 to all of this, right? So it is clearly like X, of course, is contained in n from 1 to infinite, the union of all this open ball. So it is a open cover. So since X is compact, so we can find some n. We can find a finite subcover, right? So basically, there exists a integer n such that X is covered by this finite open cover. And this, since this ball is with the radius increasing, actually all of this is contained in the ball of x 0 n, right? So now if we let m to be 2 times n from triangle inequality of the matrix, so for all x and y in X, the D of x and y, of course, is less or equal than D of x x sub 0 plus x sub 0 y, right? This is the triangle inequality. And then this we sent, because X is covered by this big open ball, right? So this is less than n plus n, which is n. So we proved part A, right? So for part B, let's see. The part B is kind of the converse of part A, right? So if XD be a complete metric, we require XD be a complete metric space. And then if we have such M, whether, X necessary to be compact now. The answer is no, right? Not necessary, but the answer is no. But if you look at the normal, like, for example, 0, 1 open interval, it's not a counterexample, because this is a not complete. It's a metric space with a Euclidean, absolute value. It's not complete. So, but even though, for any x and y in this interval, the distance with the absolute value is less than 1, right? But it's not a counterexample. So to construct a counter example, actually we can think about the discrete topology. So we pick X is the real numbers, the set of real numbers, and we define the matrix for X and Y to be, M if X is not equal to Y, and 0 if X equal to Y. And then this is called the discrete topology and discrete the matrix, right? So we can verify it is easy to verify that D is indeed a matrix defined on this X R, right? And then now we want to validate under this the matrix, like this X is complete. So all we want to know is, like, if we have subsequence if we have a sequence in X, which is Cauchy sequence, right? So in that is to say, like for any epsilon greater than 0, there exists some n such that d of x n x m less than epsilon for all n m greater than this bigger n, right? So now if we pick if fix this epsilon equal to, for example, m over 2, then we can see that because the only case, like, we want this x sub n x sub m less than m over 2, because there are only two choices, either m or 0, right? So the only thing, like, if you want this the matrix to be less than 1 over 2, is meaning, like, after some n, there is some n, right? There is some n such that x n equal to this fixed x n if n greater than n. That is to say, after n terms, it become a constant. So of course, the constant, this goes to x sub n as n goes to infinity. That means which xn is also in X, right? So X is complete. A complete matrix space with this matrix. Now, any singleton for all x in X, which is our R, right? So the singleton set is open in X under this matrix, right? So the singleton is easy to verify because the only thing, like any open ball around X, when you have the radius small enough, it has to be X itself. So that means this is open. So now X is clearly, all this covered by all singletons, right? But this does not have a finite subcover, right? Because X is infinity, so it cannot have a finite subcover. X is not compact. Yeah, this is the counterexample, right? That's it.